We looked for problems we encountered in our daily lives. Among many inconveniences, we chose to focus on issues with delivery container. We noticed several problems. The first problem we found was that the film is often hard to peel it off. Second problem is that when we try to cut it, it's difficult to control the force, which causes the food to splash. The last problem was the peeled film rolls inward due to the heat. Our goal was to design a container that allows the film to be opened with less force, prevents food from splashing, and stops the film from curling inward. The material that we used in 3D printing is ASA material. To make the film easier to open, we designed the container using tensile force. We altered the shape so that the film can be torn with minimal effort. In our first experiment, we added a cutting groove around the container. The idea was that the groove would generate tension between the container and the film, allowing even a blunt tool to cut through it more easily. After the experiment, we found that Design Drawing 1 cuts film with less force than standard containers, and even with a dull object. However, there was still a problem. During the design, the inner attachment surface could be sealed together, just like in the original container. So the problem of removing film wasn't completely solved. To fix this, we first decided to reduce the surface of area of the inner sealing zone and change the container's height. But instead of making the height difference of the container, the design drawing was made in a way that film can be attached but easily removed by minimizing the inner attachment surface. The second experiment was conducted by manufacturing 3 different types of attachment surfaces of containers. We created 3 types of inner sealing shapes. This is type 1, and this is type 2, and this is type 3. The purpose of this experiment was 2 things. The first was to find out which shape allows easier tearing of the film, and the second was to compare whether the film remains properly attached to the sealing surface after tearing it. According to the experiment, if we list the shapes in the order of cut, it's in this order. The result showed that the M-shaped container performed best in both aspects. We thought like this because M-shaped container had one more sealing surface compared to the other shapes, allowing the film to stick better, also providing more support of tearing. Type 1 and Type 2 look similar, but the difference between the two is that the difference in tension occur because of the different spacing of attachment surfaces. In the last experiment, we compared our final M-shaped container with a standard container. We tested 2 things. First one is the amount of food that splashes when opening, and the second one is whether the film curls into the food after being opened. As shown in the video, our container allowed the film to be cut more easily and smoothly. To measure food splatter, we filled each container with water and compared the weight before and after opening. The original container lost about 0.3 gram of water, and our M-shaped container lost about 0.2 gram, indicating less splashing. The original container's film rolled up inward, so the film contacted with the food. But on the other side, because of the additional area that constitutes our container, it prevents film from getting rolled inside. Based on these 3 experiments, we concluded that our container has 2 main advantages. First, the use of tensile force allows the film to be torn with less effort, and even with blunt tools. Second, the redesigned inner sealing area prevents the film from curling inward. This also enhances hygiene since it prevents food from splash to your hand when opening the container. We have conducted market research on original packaging containers. Currently, the most widely used and commercially available containers are made of PP material. Additionally, there is little difference between retail and wholesale prices of the container. Thank you for listening.